Okay, so today we are going to look at problem number 15 from the free response packet. Again, if you have not done problem number 15, then stop this video, go do it, and then come back to it. But if you are still here, then I'm assuming that at this point you have done this problem so that no spoilers are given. Okay, let's see what we got. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume is increasing at a constant rate of 2,000 centimeters per minute. So this is important. Its volume is increasing at this rate. So in other words, dV dt equals 2,000 centimeters per, I think they said minute. Let me just double check. Yep, 2,000 centimeters per minute. That's important, right? That's the rate of change of the volume. The oil slick takes on the form of a right circular cylinder with both its radius and height changing with time. Huh, that's kind of interesting. Shape of that, right? It's kind of like this can that's like, right? That's like this kind of like, think like a garbage can that's kind of like increasing with its radius and height. I guess that's what an oil spill would look like. Huh, I learn something new every day. Okay, note that the volume of a right cylinder with radius r is given by that formula. So I'm just going to write down that formula because obviously I'm going to be needing it quite a bit. Pi r squared times h. Okay, let's move on to letter A. At the instant when the radius of the oil slick is 100 centimeters, so when r equals 100, and the height, so h equals 0.5 centimeters, the radius is changing, so dr dt is increasing, right? So this is a positive value, is increasing at, I'm just going to put a positive there to remind myself, at positive 2.5 centimeters per minute. Okay, what is the rate of change of the height of the oil slick? Okay, let's see what we can do. So I'm going to take the volume function that they gave us. So I'm going to grab this guy right here. Bam. And I'm going to take its derivative. So let's go and do it with respect to time. So in order to do this, I get, so the derivative of the left-hand side is dv dt. And pi, I'm going to pull that out. And let's take the derivative of that r squared h. Now that's a product rule. So I'm going to take the derivative of r squared, which is 2r dr dt, again, because I'm doing this with respect to time. Then I'm going to multiply it to the second function, or I'm going to multiply that by h. Then to that, I'm going to add the derivative of h, which is dh dt times r squared. So that's going to be r squared dh dt. Okay, so again, I used product rule in order to take the derivative of this right-hand side while pulling out the scalar, that constant. I'm going to clean this up just a little bit for no really good reason other than I think it might be a little bit easier to manipulate later on. So I'm going to say dv dt equals 2 pi r dr dt h. Actually, I'm going to move that h. I'm going to move it here. I think it's just going to be easier. Plus pi r squared dh dt. Okay, now at this point, it's time to start plugging in our number. So dv dt, we are told, is 2,000. And then it's 2 pi. The radius was 100. The height was 0.5. And then dr dt is 2.5. Okay. Then we get pi times the radius squared, so that's 100 squared, times dH/dt, which of course is what we are looking for. Cleaning this up just a little bit, so just kind of doing some quick multiplication. From here, honestly, right, we're just gonna solve. I'm gonna do a little cleanup so you can kind of, to make this a little bit easier for me, but really, this is an algebra problem. You're going to go and solve the algebra problem. And from here on out, I'm going to solve for dH/dt. When I am finished, and this is, again, I'm going to do this using my calculator. After I've solved for dH/dt, I'm going to plug it in and get a decimal value. I got dH/dt is approximately equal, and there's two acceptable answers, either 0.038 or 0.039, and that both of their units are centimeters per minute, depending on what you chose. I don't know if they asked for units, but there they are. Okay, let's see. Obviously, I can't answer any questions right now, so let's just kind of make sure. I want to highlight a couple things I did just to kind of review to make sure you understand. So first off, we had a position function, right? This gives us the amount of oil in the spill. We were asked to find the rate of change of the height. So in order to do that, I took the derivative of that function with respect to time. And because r squared h is a product, I used the product rule. From there, I basically plugged in my numbers and solved. Very quickly, I'm going to go over the points just so you can kind of see what they were looking for specifically. The first thing they were looking for, and I thought this was a little bit interesting, they were looking for, let's see, they gave 1 point, and I think it's more of if you plugged it in correctly, because I don't know how they would have done it, but that you knew that the 2000 went to this right here, and that the 2.5 went to this. It's a little bit awkward, because I guess it's when you plug it into your function, then that's where that would be indicated. So maybe you could say, if you wanted to kind of look at that, I'll highlight this in, let's say, green. You got 1 point if you recognized that. Okay, that's one of your points. Then you got 2 points for this right here, either this piece or this piece. In other words, you took the derivative correctly. Okay, and then finally, there was, let's see, I've done 1, 2, 3. Oh, no, I'm kind of wrong. This is real. Like I said, this is a weirdly graded problem. They gave, so let me correct that. They gave 1 point for this and 1 point for this. I think that's kind of bizarre because they basically say it, but they did. Okay, so that is a little strange, but that's how they grade this. This is a 5-point problem. I think they were stretching. So anyway, they gave a point for the two green highlighted parts. They gave 2 points for this green highlighted part, and then finally they gave 1 point for your answer. So either this or this. Okay, so a total of 5 points on that question. Let's move on to part B. Part B, what do we got? So a recovery device arrives on the scene and begins removing oil. The rate at which the oil is removed is this function that's measured in cubic centimeters per minute, where T is the time in minutes since the device began working. Oil continues leaking at a rate of 2,000, those units. Find the time T when the oil slick reaches a maximum. Okay, so if I want to figure out when the oil slick reaches maximum, I'm going to actually go and erase this stuff so I have a little bit of working room here. Okay, so let's try that one more time. So if I want to find a maximum for this function, I need to come up with the function itself. So I think you would agree that we're trying, if I want to figure out the amount of oil, I want to figure out when the amount of oil is at a maximum, right? So the way I'm going to do this, let's just kind of plan this out before I start putting pen to paper. What I'm going to do is I'm going to have to take the amount of oil going in, right? There's a function for the amount of oil going in that was given by V, and there's also the amount of oil going out, which was given by, they gave us a rate of change for that function. But basically, right, if there's oil going in, oil going out, I'm going to subtract those two functions. So let's just call for now, I know they didn't give it to us, but let's say that the function for the amount of oil going in, they gave it as capital R. Let's call it, let's say if you integrated that function, if I wanted to create a position function, we would call it little r. That's kind of weird, but whatever, little r. So for a position function, right, if I want to say how much oil is in at any one time, I would take the amount going in and subtract the amount going out. Okay, I hope that makes sense. Now, I want to find the maximum. When is that at a maximum? So what am I going to do? I'm going to take the derivative of this function. So if my original function is v minus r, then what I'm going to do is I'm going to take the derivative of that function, and I'm going to find the maximum that way. So in other words, I'm going to need to know what is the derivative of the volume, which we did in part A, and I'm going to need to know what is the derivative of the amount going out, which they gave us right here. So putting that together, let's go and put that together. Hopefully that makes sense, the logic at least. So I need to know what is the rate of change of the volume of the oil going in. Well, they told us, right? It's 2,000 cubic centimeters per minute, then that's constant. So I'm going to say it's 2,000 cubic centimeters per minute. Then I want to subtract the rate of change of the oil going out, so minus R of T. Okay? Now, so if this is my derivative, and I want to then go and find a critical number, I think you guys agree, I'm going to set this equal to 0. So in other words, I want to know when does the rate of change volume that they gave us in part B equal 2,000. Okay? Before I continue, let me clarify one more time. So again, if we wanted to come up with a function for the amount of oil in the ocean or the lake or whatever this was, right? We would have the oil going in minus the oil going out. So this would be a position function. If I want to go and find the maximum, right, of this function, then I would have to take the derivative of this minus the derivative of this. The derivative of the first, right, that they gave us. They said it is 2,000, it's a constant. So they gave it to us right here. Minus the minus the dr dt, they also gave it this. They said it's this function right here. Hopefully that makes sense. So from here on out, we're just going to go through and do the math. So let's see what we got here. So our rate of change function was 400 root t equals 2,000. So from here, I'm going to solve. So I get root t equals, what is that? 5. So t equals 25. So this is my critical value. Now, I still don't know. That could be a maximum. It could be a minimum. I don't know. So I have to go and check. So again, I'm going to make a sign chart. But again, the sign chart is what am I going to say here? The sign chart is not something that you can include on your what's it called? It's not part of your work. So let's see what we got here. So I'm going to kind of look at, in order to look at my sign chart, I'm going to use this right here. So let's kind of look at that. I'm going to bring that down, 2,000 minus, and I'm going to use the actual function they gave us, 400 root t. So if I were to plug in, let's say 1 times 1, I think you'd agree it'd be 2,000 minus 400. That would be a positive number. Therefore, we have a positive there. If I were to plug in a number after 25, right? So let's say, just to make it easy, let's say 100. That would be 4,000. That'd be negative. So we clearly have a maximum. That's an A, not a maximum. So we have a maximum there. I did it again. We have a maximum. Okay, so let's put it together because they asked us to justify our work here. So what I'm going to say, let's see. Let's say, so what I'm going to say is if the rate of change in the amount of oil in the spill is given, so I'm talking about the rate of change of the oil, right? So I'm going to say if the rate of change, if the rate of, how do I want to say this? I'm trying to like put this in a way that that makes a little more sense in terms of the way they answered it. And I'm not quite liking what I'm going to say here, but here's what I'm going to say. So basically I'm going to say, since the rate of change of the amount of oil in the, what was it? What am I looking at here? In this lake is given by this function, and then I can do my analysis. So since the rate of change for the oil in the lake and I'm gonna create a function. I'm gonna say it's given by this function. Actually, let's call it O. This part, I understand that this may be a little bit awkward in terms of its wording. It doesn't matter. Okay, I want to show that I've said that this is a rate of change and this is what it represents. Okay, the rate of change for the oil in the lake is this. Okay, then what I'm going to say, and this is where it's important, and I think this is the only thing they're looking for. So at, let's do when. So when t is less than 25, the rate of change so the rate of change of the amount of oil will be increasing. Well, I shouldn't say that. Well, it is. Okay, that is true. That is a correct statement. The rate of change in the amount of oil is increasing because, nope, that's not actually, let me rephrase it. That was a bad way of saying it. So let me try that one more time. So when t is less than 25, the rate of change of the oil in the lake is positive. Meaning, and again, I'm kind of going a little bit too far here, I feel, but I'm trying to be precise. So like I said, I'm going a little, I think I'm going a little bit too much on this. So I'm going to say, meaning the amount of oil in the lake is increasing. Okay, so I've said, hey, when the time is less than 25, look, the derivative is positive, therefore the amount of oil in the lake is increasing. When t is greater than 25, My handwriting, let me clean up my handwriting a little bit. I'm going to slow down just a little bit. So the rate of change in the amount of oil is positive. Negative is negative. Therefore, okay, so therefore the amount of oil is decreasing. So what have I established? I've established that before time 25, the amount of oil in the lake is increasing, and then after time 25, the amount of oil is decreasing. Therefore, time t equals 25 represents a maximum. Okay, again, a little bit overblown, what they are really looking for. So let's just kind of talk about what they are specifically looking for. One, they are looking for some version of this. Okay, either you rewrote it, you made a new function. So either you said, hey, I've got this new function, so the oil in the lake equals this, the rate of change of the oil in the lake equals this, right? And then you took the derivative of that. Let's move that over. So either you did something like this, or you took the derivative and you did something like this. The key is that we should be able to do this. We should be able to take our derivative, set it equal to 0, and get 25. So again, it's really the setup. Were you able to do something either like this or like this? Next. The next point is for the actual finding of the number 25. And then finally, your last point is for your justification. What they are looking for in your justification is that you actually check to see that it was a maximum, right? You didn't just say, hey, it's a critical number, therefore it's a maximum. No, what you did was you said, I looked to the left, I looked to the right, I saw to the left it was positive, I saw to the right it was negative, therefore there was a maximum, okay? It wasn't a wild guess. That's what they're looking for. Okay, whew. Part B was kind of long. Let's move on to part C. Let's move on to part C. My handwriting is really bad. I apologize about that. Okay, maybe I'll try writing a little neater this time too. Let's see if that works. Okay, by the time the recovered device began removing oil, 60,000 cubic centimeters of oil had already been leaked. Write but do not evaluate an integral involving an integral that gives the volume of oil at the time found in part B. Okay, so let's see. What I want to do is I want to come up with a displacement function. So the first thing we're going to do, I'm going to start at time 0, right? At time 0, there's 60,000 cubic centimeters of oil. So that's what we're starting at. So I'm going to say, here we are at time 0, right? That's how much oil we have in there. Now, what's going on? We're going to have to take that displacement. So now what I'm going to do is I'm going to add that displacement. So from time 0 to the number that I found in the previous example, which was 25, right? And then I'm going to take the function for the amount of oil in the lake, right? Well, the amount of oil in the lake is, well, it's going to be the integral of dv dt minus that other function that they gave, minus that other function that they gave us, right? Because again, this represents the rate of change of the volume of the oil going in. This represents the rate of change of the volume of the oil going out, okay? And that's it. That's all they're asking for on this one. So now you might be saying, well, I'm adding it, but what's going on here, right? At some point, so let's think about in the beginning, right? From time 0 to 25, I think you'd agree the amount of oil is increasing. So we have 60,000 plus this displacement, which is going to be a larger number. So we're going to get a larger number. But after time 25, right, this whole value here is going to, this value here this amount is going to start decreasing. And so obviously the hope is, so we're going to be at, let's say we're at 80,000, but then we're going to go down to 70,000, 60,000, dot, 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 dot. That's the idea here, right? So this value here can be both positive or negative depending on its displacement, whether we displace a positive amount or we displace a negative amount. Okay, that's all there is to it. Again, I do want to remind you, if you have any clarifying questions on that, please make sure that you ask them during the Zoom meeting so that we can take care of them. Otherwise, again, as always, please make sure you do not like, comment, or subscribe, and I will talk to you later.